Okay, so we will look at types of solutions today and then how to express concentrations. The first slide that you see there says suspensions or mechanical mixture. It's the same thing, but most commonly we call it a suspension. So you've dealt with suspensions, especially when you were little and you wouldn't swallow a pill. Your parents would smash it up and they would put it into something for you. So maybe they like mix it into honey, they put it on a teaspoon for you, or maybe ice cream, and then they had you eat it, and then you took your medicine. Did that happen to you guys?
No.
Applesauce, that's a very common suspension. You still do that. That's, yeah, you make yourself a suspension. So I did this, or my kids have had this, and when you go to the doctor, sometimes they have to make you a suspension. If there's not a liquid form of that medication, the only way to make it into a liquid form is to smash it up and then to suspend it, hence the word suspension, in some sort of liquid that is very viscous. So the reason why you need a viscous liquid is so that it holds the particles in there kind of momentarily. So when you read bottles that say shake vigorously or make sure you shake before you take them, is because otherwise the solids are going to sit down at the bottom. And when you take a spoonful of whatever the medication is, you're actually just taking the syrupy part and not actually the medication, because the medication's at the bottom. So when you shake a suspension, the pieces disperse all throughout the solution or throughout the suspension, and you're taking a sample of it. Now, your sample parts could be different. So maybe the bottom is a little bit heavier with substances than it would be at the top, so you might not get the same dosage. But a suspension allows you to take solids sort of in a liquid form. So it gives you there in your notes, it says it's a heterogeneous mixture. An example would be sand and water. And then most important is that you recognize that the size, the shape, and the concentration of the particles can vary depending on the shaking, depending on the crushing of the solids, where they might end up. The next one is a solution. Let me try to get this on. A solution is a homogeneous mixture, so you cannot see the parts. Everything is dissolved in one another. The concentrations do not vary. So you would not find that the top is different than the bottom or anywhere else. They would be the same concentration throughout, and you don't need to shake it because all of the components should be evenly distributed. Filtration is something that we talked about for both of them. You could filter a suspension, but you can't filter a solution because everything is dissolved. Hey, it's working. All right. And then the next part is solvent and solute. So we've used these words before, mostly with solids and liquids. So we would say that the solvent is the substance being dissolved, but that's only true if you have a solid. And then this is the solute. I'm sorry, I wrote the wrong thing. Sorry, I wrote it in the wrong spot. The solvent is doing the dissolving. And then the solute is the substance being dissolved. That's typically what we consider it, but that's not necessarily true to think of it that way if you're considering liquids with liquids or gases with liquids, because you don't have an actual substance that's being dissolved. So the way that you should really consider it is that the solvent is the substance that there's more of, and that the solute is the substance that there's less of. So say I have alcohol and water, and I have like a bottle of alcohol, something with an OH on it, and then I pour in, this is 100 milliliters of alcohol, and I pour in 5 milliliters of water. So which is my solvent, which is my solute? Alcohol is the solvent, and then this is your solute. And then I could switch those ratios, and then the terms switch, right? So it just depends on which one's more plentiful. So if we talk about this in terms of gases, I could have a volume of gas like 10.0 liters of neon gas mixed with 9.9 liters of helium gas. This still is my solvent. This is still my solute. So it's just whichever one there's more of, we consider the solvent. All right, a saturated solution. Very important that you understand this, because the AP exam will typically give you an entire problem, and the key word to solving the problem, which we'll get to in the next lecture, is that it's a saturated solution. So you need to know what a saturated solution means. And so we did this a little bit in Honors Chem. So we have three different scenarios. we have saturated, we have unsaturated, and we have supersaturated. So in an unsaturated solution, I can dissolve more stuff. More can be dissolved. And there is no solid sitting at the bottom. That's key. So if I dump in sodium chloride into this, I end up with Na plus and Cl minus ions, and there's nothing sitting at the bottom. That's not saturated, right? It means you can dissolve more. All right, the next one would be a saturated solution. So I dump in my sodium chloride, and I put 1 drop extra, 1 more crystal of sodium chloride, and it comes right down to the bottom and falls out. So no more can be dissolved. You've reached your maximum concentration in that solution, and we call that saturated. So solid at the bottom. The next one is a supersaturated solution. In a supersaturated solution, I have sodium chloride dumped in, and I have ions floating around, but there's no solid at the bottom. It holds more than should be allowed. So it holds more ions in solution than allowed. And also, I forgot to write my ions in this one. You have ions in all of them. So if a solution is saturated, it is literally like if you were making yourself lemonade, and you dump in some sugar and you stir it up, and it all dissolves, and then you dump in some more and you stir it up, and now like a little bit sits at the bottom. But then I dump in even more. What happens? A lot goes to the bottom. It can't dissolve anymore. So it doesn't matter how much more you put in. Once you've reached the maximum concentration of the ions that are allowed in the solution, it can't hold any more. It's as if we're going into a theater and the theater holds 25 seats. And 25 of us walk in, and then 2 extra people walk in. There's no seats for them. It doesn't matter if 2 more people walk in or 50 more people walk in, there's still going to be only standing room, right? So if I dump in 1 gram of sodium chloride or I dump in 100 grams of sodium chloride, once I've reached the maximum concentration of the ions in the solution, the rest just falls to the bottom. So I would end up with a large amount. You need to write that down. So once the max concentration of ions is reached, the rest falls to the bottom. You know what I mean by the rest, right? The solid falls to the bottom.
How come for a supersaturated you wrote no solid at the bottom?
We'll talk about that in a second, but there won't be.
Okay.
So here I could add more. This, it doesn't matter if you add more, it's just going to sit at the bottom. And then with the supersaturated solution, the way you get a supersaturated solution, we'll get to this later, but you heat it up. So basically, say I put sugar into my lemonade and no more is dissolving. If I want more to dissolve than should be allowed, I heat it up, and then the solution will accept more. We know this because I'm going to talk to you in a moment about equilibrium a little bit. What is the only thing that affects equilibrium constants? Temperature. And dissolving is an equilibrium system. So if I adjust the temperature, I can drive it to make more products, which essentially are more ions in solution. So dissolving is an equilibrium system, and we discussed Kc, Kp, and and Keq so far. But with this section, we're going to still use equilibrium, and we're going to discuss what's called Ksp, which is the solubility product constant. So when we have something dissolving, that's what this is showing you. Say this is sodium chloride that I dumped in. It dissolves into its individual ions, but it does so in an equilibrium state, where it produces the max number of ions that it should produce, but then it actually goes backwards and produces the solid. So we don't really ever see that occurring. We just see solids sitting at the bottom, right? But it is actually going into solution, forming ions, and then the ion concentration is too large, so it falls back out of solution into a solid, and it does this sort of repetitive pattern. The way that scientists figured that out is they used radioactive isotopes of the materials that they were putting in to dissolve. And you can measure alpha beta particles and gamma particles. You can measure those, and you can determine where they are in the solution as they go into the solid and back out of the solid and into the solid and back out. So they actually saw equilibrium occurring in the solid and aqueous states. Any questions on that? Okay. Types of solutions. So we're going to have liquid-liquid. We know solid liquid already. Liquid-liquid, gas-liquid, and then gas-gas. So you need to remember that we've discussed this before. The way that things dissolve in one another is like dissolves like. Do you remember that? Jot that down again. Like dissolves like. So if I'm a polar substance, I'm going to dissolve something that is polar. So polar dissolves polar. That's what like dissolves like means. Non-polar dissolves non-polar. Dissolves means that it's going to completely break it apart into a solution. So you wouldn't see parts. It would be completely mixed in. So what this slide is showing you is that you have methanol, and then anything with an OL means that it's an alcohol, which means it has hydrogen bonds. So just make sure you jot that down. Anything that has an ol ending, like methanol, ethanol, isopropanol, those all have OL endings. That means that it's a hydroxide group off the end, which is hydrogen bonding. These are H bonds. Methanol has one carbon. This is methanol, with 3 hydrogens off of it, and then the ol group. All right, so you should be able to identify why something dissolves in something else. So the questions you're going to see will be multiple choice and free response, where it'll say, which of the following would best dissolve methanol? And then I give you 4 choices. So you're looking for the substance that is most like methanol. What is the most contributing factor of methanol? What kinds of intermolecular forces? Hydrogen bonds. So when you go to look at your list, you're looking for something that is like each other. So you're looking for hydrogen bonds. Something that has more hydrogen bonds would then dissolve it better. So methanol and water are completely miscible, and the word miscible means that they dissolve or they're soluble in all proportions. So you need to know that vocab word. Miscible means that they are soluble in all proportions. It doesn't matter if I use 5% water and 95% methanol, or vice versa, they will completely mix with one another. So mix in all proportions. A miscible solution never becomes saturated. Nothing ever falls out of solution. It's just going to be mixed. It doesn't matter how much you put in. If I put a drop of methanol into water, it dissolves. So it says differences in intermolecular forces can cause the solution's volume to differ from the sum of the volumes before mixing. This phrase right here is so important for these questions. This is what this means. This statement is telling you that sometimes you can mix 2 liquids and the liquid volume contracts. I don't know that you've seen this so much. I've definitely seen this when I'm measuring stuff. The volume liquid can contract or it can expand. So if I'm measuring in a graduated cylinder and I put 5 mils of one substance and then I pour 5 mils of another substance in, I should expect it to be 10, but it turns out to be like 9.8. That's because the volumes, they have strong intermolecular forces of attraction and they squeeze and hold each other tighter, whereas others can expand their volume. So the AP exam doesn't want you to have to deal with that, expansion and contraction. So what they do is they give you basically this statement, and this is what they say. They say, assume, first word they write, they always write the same sentence. Assume volumes are additive. If they're telling you that a volume is additive, that means you better add the volumes, because if you don't, you're going to get the answer wrong. So if I say I use 50 milliliters of a 0.1 molar solution and 50 milliliters of another, so let's say 1.5 molar solution, what's my total volume? 100. I'm telling you that this is like ridiculous to even mention it to you because you said, well, that makes so much sense. But so many of you use 50 because you're like, oh, it's the same volume for both substances, so I can use just 50. But you have to add your volumes. And they give you that clue because the final sentence almost always says, assume volumes are additive. Okay? So that's what that means. Just add your volumes up and nothing contracts or expands. All right, your next type of liquid-liquid solution. I gotta erase all of this stuff. All right, this is hexanol. So what do you know about it? It has hydrogen bonds, but it says to you that it is not miscible, which means that it does not mix in all proportions. Like at some point, you're not going to be able to get them to completely mix in one another. So not miscible means they do not mix in all proportions. So it says some hexanol will dissolve in water, but at some point you're going to get there where it's not going to dissolve anymore. And so it's limited based on its nonpolar chain. So hexanol has an H bond, right? But look at water compared to hexanol. Hexanol has 6 carbons in a long line, which is all nonpolar, right? The only polar piece is the OH end on it. So yes, you can get some hydrogen bonding with water, but water would prefer to stay with itself because like dissolves like. So water is going to stay with water primarily most of the time, and then it'll mix a little bit with the hexanol, but that long carbon chain is going to stay with the long carbon chain. And you will actually see, this is sort of a good example of it, but it's not this. But if I shake this up, and you can literally see, like, once it separates, it's cloudy. Can you see that? Like, it's not clear anymore, and it's sort of like this murky little area. That happens all the time when you mix a polar and a nonpolar substance together. They're trying to, like, kind of fight their way apart, and because they're not miscible, you see that sort of murkiness. That happens sometimes with liquids. You'll end up with, like, this hazy region right here, and then this will be clear, and this will be clear, and this is, say, a nonpolar substance, and then this is a polar substance, but right in the middle here, they're mixing for just a little bit, and you'll literally see like a murky area where they're trying to bond with one another. That's sort of what you would see in this case with hexanol and water. All right, so the rule is more than 3 carbons, we say that it is not miscible with water. So with water, it's not miscible. So if it's an alcohol, if it's not an alcohol, then it would still be nonpolar with polar. So with more than 3 carbons, I should say an OH, an all, with more than 3 carbons is not miscible. 6 or more carbons, we say is completely not soluble. Not soluble. And again, these are with water. So what does not soluble versus miscible mean? Or wherever the density would lie, but it would not dissolve or mix at all. So they would just completely separate one on top of the other based on density. Whereas with the 3 carbons and an all, you might get a little hazy region of mixing. Some mixing would occur. So the way that you're going to identify, you have to look at each component and say, is it polar or nonpolar? What are the main contributing factors here? And then remembering this sort of 3 and 6 rule. All right, here's another example. That's hexanol with hexane. Do you think those dissolve without reading it? Mm-hmm. Why do you think that's true, that they would dissolve in one another? They're both primarily nonpolar. I just told you 6 or more carbons is really not polar enough to even mix with water. So it's certainly more nonpolar than it is polar, right? So the contributing factor to this is that nonpolar mixes with nonpolar. They both have London dispersion forces, and then they'll mix together. You have to be able to identify that. So if I say hexanol would dissolve best in which of the following, and I list water, and I list C6H14, and I list maybe like C18H whatever. The most nonpolar with the most nonpolar are going to mix with one another the best. Does that make sense? So water is not a good option for this. It's not going to dissolve very well in that. All right, solid liquid solutions. So we're going to go back to our intermolecular forces a little bit and discuss that. That's why I do that so early on with you, because we really talk about it all year long. When you dissolve a solid into a liquid, you have to look at what the solid is. It could be that it's not ionic. You could have a molecular solid, like glucose is a molecular solid. That still dissolves in water. It dissolves in water differently than ions. The glucose molecule gets surrounded by water molecules due to hydrogen bonding, and it pulls it apart to dissolve it, versus ions get pulled apart through ion dipole. So you still have to be able to figure out the two pieces. So you identify the type of particle that the first substance is. Is it polar or nonpolar? If it is polar, does it have hydrogen bonds? You identify what kind of particle the other one is. Is it polar or nonpolar? And then you can determine how it dissolves. So an ion dipole, again, is an ionic compound in a polar solvent. That's what we call an ion dipole. Polar solids, such as glucose, dissolve in polar solvents like water. We call that a dipole-dipole. If they both have H bonds, then we call it hydrogen bonding. And then nonpolar solids, such as mothballs, the correct name for mothballs is naphthalene, dissolve in nonpolar solvents, and that's just London dispersion forces. Do you guys know what mothballs are? I feel like this generation is like leaving the mothball phase. Like your grandparents don't use mothballs anymore, so you guys don't know what they are. But my grandparents used mothballs, and then like after me, your grandparents are too young, I feel like, at this point. But prior to, I don't know what decade, you history buffs should know, most of our clothing was made of wool. Like we didn't have nice like nylons and silks and all cotton blends. We primarily used wool, especially for coats, right? And so in my grandmother's closet, it is such a distinctive smell. Every time I went into her closet to get the stool, because I sat on this little stool at her house, and she would feed me. Always, I would have orange juice at her house. She would say, go get the stool, and I would get the stool, and I would go sit at her house. And I opened up the cabinet, or the door, or closet where it was, and it would be like, it just hit you so hard. It's this stinky smell. Have you smelt it? Of mothballs. You should just buy a box of mothballs so you know what it smells like. I mean, it's something that many, many people can recognize that smell. And it's literally a ball of naphthalene. It's like a solid. It almost looks a little cottony. And it keeps moths away, because what did moths do? Eat the wool. So the moths would eat holes through the wool coats, and then people would have holes all in their clothing, which they didn't want, right? So then they would put these mothballs in their closets, and then they wouldn't have moths in there eating holes in their clothes. But instead, what do they have? Really stinky clothes. Like it was just this weird thing. Like everyone smelled like mothballs. Anyway, I bet you don't learn that in your history classes. Yeah, there's like a whole, I don't know, decades worth of people walking around with stinky coats. They smell like mothballs. But that's what you did to keep your clothing intact. So anyway, that's what mothballs are. Did you ever hear of a cedar closet?
Yeah, I have a cedar closet.
I have a cedar closet also. Why do you have cedar closets? To keep the moths out. So if you didn't want stinky clothes, people built cedar closets so that they could keep the moths out. And it keeps like the moisture very low in there so that your clothing stays fresh. It doesn't smell mildewy, all that kind of stuff. All right, moving along. So we have also gas-liquid solutions. We know that fish breathe oxygen in water. How does oxygen gas get in there? How do we make soda? We pressurize a bottle of sugar water with carbon dioxide gas, and we can get it to go into the solution. So do not call out what kinds of intermolecular forces are present in both of these. So remember what I just said. Identify the substance and what types of forces it has. Is it polar or nonpolar? Identify the other substance. Is it polar or nonpolar? And then determine what kind of forces cause it to be miscible. All right, what kind of properties does water have? H bonds, and it's polar, right? That's key, is that it's polar. The first thing you're doing is always identifying, is it polar or nonpolar? That's key. And then, yes, it has hydrogen bonds and London dispersion. All right, what is carbon dioxide? Nonpolar, right? If you're not sure, you have to draw molecules. It's nonpolar. So how do I get carbon dioxide to dissolve into water? What's that intermolecular force that we jotted down a long time ago? Good job, Rob.
Another 18 for you.
Dipole-induced dipole. Do you remember that? A dipole-dipole is when they're both polar. When you have a polar and a nonpolar, that's dipole-induced dipole. When you have an ionic compound and a polar compound, that's ion dipole. When you have two nonpolars, that's induced dipole, but we have that special name called London dispersion forces for it. Do you get it? We wrote this down back in your intermolecular forces unit, so if you don't remember that, pull those slides out. So I'm going to say it again. Polar with polar is dipole-dipole. Polar with nonpolar is dipole-induced dipole. And then nonpolar with nonpolar is induced dipole, but we call it London dispersion forces. And then ion dipole is an ionic compound with a polar compound. You getting this all? Yep. What is oxygen? What's that force that causes it to go into water? Oxygen gas goes into water. That's what aqueous means, is that it went into water. What's the property that makes that dissolve in water? Hello? So you guys are confused again. What? Thank you. You got, was it Rob again? Look, you just have to identify each component. Is O2 polar or nonpolar? Nonpolar is water, polar or nonpolar? Polar, so polar with nonpolar is dipole-induced dipole. What forces make KBr go into aqueous solution? AQ, what does that mean? That it's mixed with water. How did KBr go into water? Ion dipole. Getting it?
Got it.
How do I get O2 to dissolve into N2? Because air is primarily nitrogen gas with oxygen gas, which is called
London dispersion.
London dispersion, because it's induced dipole, right? Now you get it. Right, Maddie? All right, gas is infinitely soluble in one another based on whatever intermolecular forces we have, which this just makes sense. All gases dissolve because of diffusion. I lost the word for a moment. Diffusion. When gases mix, they diffuse. They can mix in all proportions, all ratios. Gases mix no matter what. All right. Gas-solid solutions. You probably didn't know this happens. So you can literally use a solid as a filter to get gases to separate. So if I take a mixture of gases, like hydrogen and nitrogen and carbon dioxide, I take an air sample, I can push it through different metals. And so the examples here are iron and palladium. I mean, I don't know all the examples that they would use, but the point is that there's small, what's called an interstitial space in between the atoms. So we know that metals only hold on to each other through the sea of electrons, right? So your atoms are here, and then the electrons are surrounding them, and they're attracted to this one, and this one, and this one, and this one, and then they start moving around, and they just keep it all kind of tight together due to negative and positive attractions. But there's still space where all those electrons are kind of moving around. You can push through gases that go through those spaces. Since the spaces are so small, we can separate particles based on their size. Hydrogen's really, really small, isn't it? So I can get hydrogen gas to actually push through a metal and come out the other end separated from all the other gases. So like, for example, nitrogen gas would be too large to fit through this metal, so it would never make its way through. It's like a filter, essentially. two words that you have to know. One, it'll be on this slide, and then 2 slides from now. An interstitial alloy and a substitutional alloy. What is an alloy? A blend of 2 or more metals, right? We just mix them up. That's what an alloy is. You mix them up, you melt them in a pot. I don't know how else you make them. You mix them together, okay? Whenever you have an alloy, it is typically stronger than its, I guess, individual parts. Like the lowest properties would be enhanced because you now mix it with something better than itself. So an interstitial alloy, like this example is steel. Steel, we know, is incredibly strong. We don't build bridges with iron, we build bridges with steel. Steel's properties are much, much stronger than iron on their own. Iron, just like all the metals, has its own little spaces like we just discussed. But what they'll do is they'll fill the spaces with carbon atoms, enough of them so that it doesn't expand the structure, but it keeps it tighter. So you know that things become brittle when there's like air in between them, right? If there's too much air in something, you could actually like break it easier. But if you can fill in all those spaces, then it won't basically collapse, right? You've probably built things, like thinking of Legos or anything that you've built. The more solid your structure is, the better it is. So you can fill in steel with carbon, and that's called an interstitial alloy. So interstitial means that you filled in the small spaces. Got it? So this is just showing you how steel is more rigid, less malleable, less ductile because the carbon sits inside there. And then it creates directional bonds. Directional bonds are head-to-head. That's what that means. Directional bonds are head-to-head. Whereas just iron by itself would just be sitting and sort of attracted to nearby atoms, but you actually create head-to-head bonds with the carbon atoms. All right, the next type of alloy that we have is a substitutional alloy. That's really simple. Substitutional means you replace one atom with another. You substitute it. So if you're watching sports, you substitute someone, you replace somebody else. So you're just taking, for example, this is brass. You mix copper and zinc. Some of the copper atoms and some of the zinc atoms mix, and there's nothing in between them. They're just kind of all holding on to each other through the sea of valence electrons. Make sense? Substitutional, interstitial. All right, now we're moving on to the math. So we're only going to get through molarity today. Like I said before, we're going to have someone from guidance come in to talk to you about AP stuff. So I think we probably have like 5 more minutes to get to molarity. You're doing questions 1 through 12 tonight. They should be easy for you. You've done molarity before. So most important thing is that you just recognize your calculation for molarity is moles over liters always. They would like to give you things in milliliters. So just make sure that you do divided by 1,000 milliliters to give you 1 liter, which means that you move your decimal 3 decimal to the left. All right, this is new for you, mole fraction, but we will use mole fraction a little bit now, and then we'll use it quite a bit when we get to gas laws. But mole fraction, literally, again, just like any percent composition or anything that we're doing with percent, is a part divided by a whole, and then we multiply by 100, but a fraction means don't multiply it by 100. That's all we're doing. So you're going to calculate the moles of the part divided by the moles of the whole. So if I tell you I have all these different substances in a beaker, they're gases perhaps, then I would combine the total of all those moles, and then I would just do a simple calculation here. Mole fraction is represented by an X. If the question says, what is the mole fraction of helium, you write X of He equals, and then you can put 0.5. There's no unit here. It's just a fraction. So you write X as the mole fraction, and then the substance that it is a subscript. So like X of helium, I just did that. X of hydrogen, X of sodium. That would be the moles of sodium over your total moles, whatever they are. Following? So mole fraction is represented by an X, and then the subscript of whatever the substance is that you're finding it of. All right, just really fast, let's do these. 3.75 gram sample of sodium chloride dissolved in water. The total volume of the solution is 768 milliliters. What's the molarity of the solution? What's your first step? You have to find moles. So you're going to go grams to moles first. So 3.75 grams, and then you're going to use the molar mass of sodium chloride. I'm going to throw it up there for you since you know how to do that already. 0.0642 moles of sodium chloride. Anybody unclear with that? No, that's super simple. All right, so now I calculated moles. How do I calculate molarity? Concentration. That's what molarity is, concentration. You take your moles and you divide it by? What number? No. 0.768. Right, this is super simple. This is milliliters. I divide by 1,000 to give me liters. You move your decimal 3 to the left to give you 0.768. I'm just going to get to the same spot as the other class. All right, so just divide the two numbers and you get your concentration. So let's make sure that we pay attention to sig figs when you're doing this. This has 3. This one has 3, so my answer should have 3. And then capital M is for molarity, and then you write it for the substance that you're finding it of, right? So that's the concentration of sodium chloride floating around in there. What's the concentration of the sodium ions? Just sodium. So you're confused, but look. Sodium chloride goes to Na plus and Cl minus. If this is the concentration of sodium chloride, it's in a 1:1:1 ratio. So it's the same thing. What's the concentration of chloride? Same thing. What if I gave you MgCl2? And this was the concentration of MgCl2. What's the concentration of Mg? Same thing, but what's the concentration of the chloride? Double. Do you get that? So we will get to concentration of just ions also. All right, 2 more. We'll do them together. How many milliliters of a 0.245 molar sodium hydroxide solution are needed to deliver 1.75 moles of sodium hydroxide? So you're just rearranging your equation. You have molarity is equal to moles over liters. I'm just going to plug it in. 0.245 molarity equals 1.75 moles over liters. Super easy. This is just reminding you of stuff you already know how to do before we move on to harder stuff. So the question asks for milliliters, so what do you need to make sure you do at the end? Multiply by 1,000. So 7,140 milliliters. Good? When you look at these slides, they're going to look different because I don't do it that way. I would just set it up like this, like I just had it, and write 1.75 over x and solve, and then multiply that by 1,000. This is using dimensional analysis, and this is using it as your molarity. I just wouldn't use dimensional analysis. I would just use the simple equation. All right, last one. Dilution. So there's 2 ways to solve dilution problems. So this is exactly like, think of, I have apple juice at home for my kids in the fridge, and I want to dilute it because I don't want them drinking all that sugar, right? Apple juice is like almost as much sugar as like a soda. So instead of buying the light version of apple juice that they sell at the store, which is just added water, I dilute it myself. And I literally write on my bottle, diluted, so that my family knows not to add more water, otherwise the kids won't drink it. So I take the apple juice out and I pour water in. So I'm taking the amount of sugar that's in the original volume and I'm diluting it with water so that I have less sugar in the next one, right? That's called M1 V1 equals M2 V2. That's a dilution equation. However, I could just calculate the moles of the first scenario and use them in this second scenario. That's essentially what you're doing here, but I'm eliminating the word mole. Because molarity equals moles over liters, the moles in both of these scenarios will be the same. So I'm going to use M1 V1 equals M2 V2, but you could do it a different way. So important thing is that you read your scenario and you know your initial volume and your initial concentration, and that you recognize that V2, this is the tricky part, is your total volume always. This is what you want to end up with. So if I'm diluting my apple juice to 1 liter, the total volume is going to be 1 liter. I'm not going to incorporate how much water I added. So say I take 500 milliliters of apple juice, and I'm going to dilute it to 1 liter. My V1 is 500 milliliters of apple juice, but my total volume is 1 liter, 1,000 milliliters. You don't ever incorporate the amount of water you use. So I'm just going to show you how to do this one, and then we'll listen for some AP stuff. So first, suppose you need to prepare a 100 milliliter solution of 1 molar ammonia using this concentration, distilled water and a graduated cylinder. So this is my V2, that's what I want to end up with. This is my M2, that's what I want to end up with. This is my M1, that's what I'm starting with. Does everybody see that? So I'm going to take my M1 as 1.25 molar. I'm going to multiply that by V1, but I'm not sure how much of it I should use. And then that's equal to 1.00 times 100 milliliters. You don't have to convert to liters because my answer will then just be reported in milliliters. So you multiply, and then you divide, and then that'll tell you the volume that you should use of the concentrated substance. And then if we were going to solve, we would say, or write this out, we would say, pour 80 milliliters of the concentrated solution into the graduated cylinder and fill to the mark with water. The mark is 100 milliliters. So did I ever write 20 milliliters in this? Never include the 20. So you're using 80 milliliters. This will give you 80 milliliters of your V1, your concentrated amount. That's it. That's all you're doing tonight, is just using this dilution calculation. Okay. Okay, so we did this quickly yesterday, but we'll do it one more time. It's calculating mole fraction. So mole fraction is, yes, when she gets back. Mole fraction is frequently asked on the free response. It's sort of like a free point, and you should be happy when you see it. But you just have to know how to handle it. There's lots of ways to find moles, right? You can find moles from grams. In this case, we can find moles from kilograms. The other way that they'll give it to you is using gas laws, which we haven't gotten to yet, but you can use PV equals nRT to find moles. So any variety of moles, molarity, grams, and then PV equals nRT are the most common ways that they will give you moles, and then they'll ask you to find mole fraction. So mole fraction always is just part divided by whole. You did it last night in homework, but this is just a new variety. And then someone asked earlier, do I leave it in a fraction? No, you write it as the decimal. And then make sure your x is large. So go ahead and try and solve this. It says, find the mole fraction of each after you dissolve 1.5 moles of potassium hydroxide in 1 kilogram of water. So your particles that are floating around in solution are potassium hydroxide and water. So you need to know moles of potassium hydroxide, which it gave you, and then moles of water. So convert kilograms to grams, and then grams to moles. Okay, so let's check your answer. You went from kilograms to grams, grams to moles, and then
Divide by small, multiply by
no.
whole.
You find mole fraction of potassium hydroxide. But what could you do? Instead of finding mole fraction of water, you could subtract from 1. Why? Because fractions add up to give you 1. Like percentages add up to give you 100, right? Out of the total is 100%, out of a fraction is 1. So if you wanted to, you could just quickly subtract from 1 to get that answer, or you could do the problem again. Make sense? You guys are writing down a lot of information. I thought you solved already.
Well, I only went grams. I didn't do all this.
Oh, okay. Oh, no.
0.974 is the mole fraction of water, which I could have just then taken 56 and divided that by 57.5. That's the same thing. Yes, Hannah.
Remember that account for sick phase? Because like for the second one, I got just 0.97 because what I did like the actual one, I didn't just do the
Sig figs, when you subtract, is least number of decimals.
Yeah, but I did the division one. Like,
Oh, if you did division, then yeah, it would have been just 2 sig figs. You're right. Good catch. All right, things that affect solubility. So the rest of lecture is pretty simple. We're just going to go through things that you sort of know already. We're going to touch on chromatography kind of extensively, but this stuff you already know. Things dissolve. Solubility is the ability for something to dissolve. So if I want to find out the solubility of something, I would go look in the Handbook of Chemistry and Physics. I would flip to whatever substance it is, and I would check the solubility of that substance, and typically they're going to give it to you in water. But there is solubility in every type of substance, like solubility in methanol, solubility in ethanol, And then solubility is completely temperature dependent, which I'll show you in a little bit too, but you know that. Things dissolve better typically when you heat them up. So if you're looking up solubility numbers, that's going to be a specific solubility in a specific substance at a specific temperature. So the tables are endless. You have to kind of just look for information if you're trying to find solubility of something. But typically it's in water. So we know like dissolves like. We talked about that for homework last night, how things dissolve in one another. And then temperature will play a role in solubility. So how much something dissolves is certainly going to be temperature dependent. And then pressure. So pressure, as it applies to gas-liquid solutions, gases are more soluble with higher pressure. So if I pressurize a gas, it's going to go into the liquid greater, because the way that gases dissolve in liquids is whatever the pressure is on the outside pushes it into the liquid. So right now, like my liquids, my tea, your water, they all have gases that are from the air right now, from the atmosphere, dissolved in them based on the pressure. So if I'm making soda, I take my bottle of soda and I pressurize it with carbon dioxide gas, and then in that little seal, it's highly pressurized, and so it dissolves a lot of carbon dioxide in it, which is why when you tss and it opens up, all that carbon dioxide gas comes back out, because the pressure surrounding it is just a much, much lower pressure than the carbon dioxide that was originally in there, under pressure. So these are the factors that affect solubility. So we'll get through them fairly quickly. You did this yesterday. Vitamin C, so these are water-soluble covalent compounds. We know that ionic compounds are soluble most in a polar compound, right? Because it's a cation, anion with a dipole. Well, when you have covalently bonded compounds, you don't have a positive and negative necessarily like a cation, anion. You have ends to the molecules. So if something is completely nonpolar, we say that it's an induced dipole by something else. But in these, we have two polar compounds. And glucose, sugar, dissolves in water. You know that. So the way that it dissolves, though, is that water comes and it pulls each of the molecules apart in that solid. You know that's a solid. You dump that into water, you stir it up, and it starts to dissolve. It's because water comes in and hydrogen bonds at 5 different locations here. And so more hydrogen bonding pulls each of those molecules apart until you don't see the solids anymore. Now they're individual molecules floating in your water that you can't see. And same thing with vitamin C, there's hydrogen bonding sites. So more hydrogen bonding makes it more soluble. All right, we're going to spend a lot of time on this slide because I typically did chromatography with intermolecular forces, but remember I changed that lab for you, and I made that fun lab where we did the intermolecular forces tricks. So you guys kind of missed the whole lecture on chromatography, so we're going to spend a lot of time on this slide, so you might want to take notes somewhere else or just scribble them all along the side. They will occasionally talk about chromatography on the AP exam. It's not that they expect that you understand all types of chromatography, but they do expect that you understand paper chromatography. So I'm going to show you like a little demo so that you understand kind of how you would set it up and what it does, and then I'll give you some application for it because you may not use chromatography right now, but you know of it. So what you have is chromatography paper. And mind you, paper chromatography is super simple. I'm going to show it to you right now, but you could extend chromatography into very expensive techniques. And chromatography literally just means that you're separating things. So I have a mixture of substances, and I want to separate them all into their individual components, and I do so through chromatography, and like dissolves like. So if a piece of a molecule likes a piece of what we're going to call the mobile phase, which is the liquid phase, it'll stay and interact with that. If the molecule likes the stationary phase, then it stays and interacts with that. It could be paper or something more advanced called liquid chromatography or gas chromatography. So the 2 words you need to know are mobile phase and stationary phase. So your mobile phase is always going to be your liquid phase that's going through or the solution that's going through, and the stationary phase is typically a solid. So your solution, or your molecule I should say, your molecule will interact with one of those based on like dissolves like. It's going to choose something over the other because they're always going to be 2 different substances. So if your molecule likes the mobile phase, it's going to travel with that quickly. If your molecule likes the stationary phase, it's going to stay in that more often. And then as it goes through, whatever it is, paper or a column, you come out and you can detect it because it's separated by each substance. So you would have like an A plus a B, and then it would interact, and they would interact differently, and then in the end you would have an A, and then you would have a B separated. So I'm going to show you with chromatography. You probably have done this at some point, where you take a piece of chromatography paper, which is just like paper, and this is considered your stationary phase. So your molecules are going to choose to either stay with this paper, which is made out of cellulose. It does have hydrogen bonds on it, or it's going to choose to stay with my water. So I'm going to put a little bit of water in here, and water is very polar, we know that. The water is more polar than the stationary phase. So if my molecule likes to be more nonpolar, say, it's going to stay with the stationary phase, and if it prefers to be with the water, it's going to travel with mobile phase. So what you do for paper chromatography is you just mark a line on the bottom of the paper that's above the solvent line, so above the water. So you kind of just measure to make sure it's not going to fall into the water. And then I'm just going to take markers and I'm going to blot them. So I'm just going to put literally a dot on the line of each of these. And I'm going to see the molecules in the dye. So I have blue dye, green dye, orange. They're going to travel at different rates depending on the type of molecule the dye is, whether or not it likes the water or the stationary phase better. So you got to just drop it in. It touches the water. And the water, since it has hydrogen bonds and the paper has hydrogen bonds, it immediately begins to travel up the paper. So you're going to start seeing it moving those molecules up the paper with it. And it literally will drag them through if it prefers to stay with the mobile phase. So I'm going to let this go for a minute or so, and then I'll let you look at it again in just a minute. So I'm going to show you how this applies. What we do is we look at how far each molecule travels to determine what the molecule is. So that's what this is saying. The distance traveled by A, the different distance traveled by B. You can separate them. So these are two different molecules. I think this is saying this is B and this is A, and they were mixed initially, but now they're separating out. So we measure something called an RF value, but you don't really need to know that. That's just the distance that they traveled versus the distance of the solvent traveled. And then you can compare them. So what you typically do this in a lab is you compare it to a standard. So a standard is something that you think it is, or that you know it is, and you're just making sure that it's there, or you're testing it sort of forensically. Like you want to know if there's a certain drug in this sample. So you run a standard of a few drugs, and then you run your sample, and if the lines meet each other, then that's a good indicator that it's in there. This is not a quantitative test, right? You can't calculate numbers from this. It's qualitative to tell you, yes, it's present, or no, it's not. So the most common application for this is a pregnancy test and a drug test, an at-home drug test, because what you have at an at-home pregnancy test or a drug test is you have chromatography paper in some little contraption, plastic contraption, and then you have a pea stick, right? You know how all these things work, whether or not you've used them, correct? I'm sure you've seen them or watched a commercial on TV. And in the window, I'm going to use this as a pregnancy test. In the window, it tells you if you're pregnant or not. So the way that this works is you pee on your stick, and this piece of paper is literally in this window, and it goes all the way up. Sort of like my chromatography paper that I'm showing you right now, right? So what they typically do is they have one line here, and this is the control. The control means the test worked. So everybody has all sorts of molecules present in their urine, men and women. So we're just checking to make sure the test works. So I don't know what the control is that they use, but maybe it's like they're looking for potassium, something really simple, right? That everybody has in their urine. So what they will do is this will turn color with an indicator. You know what an indicator is? You put like a little drop of a chemical in there, and we've done this before. It's clear if it's acidic, and then it turns pink if it's basic. We've done that with the Windex when we make our little, we've done that, right? So an indicator changes color when something's present, sort of like in your pool chemistry. If you have a pool and you look for chlorine and you look at the color, and that tells you if it's present or not. So this will turn color if whatever it is, that's the control, is there. But then, if you're pregnant, you get HCG in your urine and in your blood. So for a pregnant woman, the day she becomes pregnant, she has a certain amount of HCG hormone in her blood and her urine, and it doubles every day. So the first day it's 2 micrograms, the next day it's 4, the next day it's 8, the next day it's 16. So it gets to be a larger number, and the test becomes sensitive enough that they can test for it. So you've seen commercials where it's like, oh, we can tell you 5 days before, or whatever they say, 3 days before. And that just means that they have a test that can detect how much HCG is present in your urine sooner than other tests, perhaps. So then, as that HCG travels up, right here is where they marked an indicator. And if the HCG hits that, that turns it the second line. So usually it's like 2 lines means you're pregnant, 1 line means you're not. 1 line means you've got the control. You have to get the 1 line. But if you get the second line, it means you're pregnant. They could make the indicator go vertical so that it looks like a plus sign, right? Plus sign means you're pregnant. If it's just a 1 line, it means you're not. So they just make the indicator change that color based on if the molecule's present, which is just like chromatography. So as my chromatography, I don't know if you can see it really well, but do you see that there's like this yellow line coming through? Not really from here. Let me grab the one that I did earlier. All right, do you see this one? You can see the red line stopped right here. So this red dye travels through the stationary phase. The mobile phase brings it up, so you can feel like this is wet with water. The mobile phase brings it up, and it's stopped right here. It's not going to travel any further. So say the HCG stops right there. If it hits the indicator, then it would change color, and you would know that you have that hormone present, which means you're pregnant. Get it? Same thing works with drug tests, at-home drug tests. They give them a cup to pee in, they stick the stick in, and the stick has indicators to change color if that drug is present. So if you're looking for marijuana or cocaine or whatever it is, all they have to do is just put an indicator where that chromatography, where that molecule would end up on the chromatography paper. Make sense? So that's how chromatography works. It's just paper, molecules travel, and they travel at different rates depending on whether or not they like to stay with the mobile phase or if they like to stay with the stationary phase. So as this progresses, I'll let you guys take a look at it, but I mean, I can see right now the blue isn't moving at all, so that means it likes the stationary phase. And then this green one and the orange one both have yellow lines sort of going up the same exact distance. That's because there's yellow in both of them. And then they'll continue to travel to separate the other colors, right? We know colors are made from primary colors. Any questions about this? Yeah.
So like say you had like less red dye, would it like knock off the star?
No. So less and more red dye doesn't make a difference. It always ends up in the same spot. I mean, if you have too little of it, it might drag it, and then there's just not enough to keep dragging it. So you do have to put a substantial enough amount that it would travel the distance that it needs to. But no matter what, it'll get there. All right. So chromatography separates molecules based on polarities, essentially. All right, the next few slides are about temperature-dependent solubility. So we usually think that things dissolve better if you heat them up, and that's almost always the case. But there are some molecules that would dissolve less when you heat them up. And that depends on whether or not it's an endothermic or an exothermic reaction. So solubility is the mass of solute that dissolves in a saturated solution composed of a specific mass of solvent at a specific temperature. So at some point, when we take a solubility value, we measure how much it can dissolve until it becomes saturated. What does saturated mean? Can't hold anymore. What do I see at the bottom of my beaker? A solid. So that's the point that I'm measuring for solubility. How much can the solution hold? So it says most of them have solubility increase when temperature increases because this process is endothermic. So think about this according to Le Chatelier's. If it's an endothermic process, heat is written on the left, right? If I increase heat, which way does the reaction drive? To the right. You have to always write your solubility reactions as a solid going to aqueous. Always. Do you remember on electrochem when I was like, anytime that you do an electrolytic cell, you have to start with the ions. Do you remember me saying that? And then you didn't, and then you got the problem wrong. So anytime you use a dissolution, or that's what it's called when you do solubility, you must start with the solid. must start with solid to write reaction. And it's a dissociation reaction. Dissociation means that you break it apart into its ions. So it should always say solid goes to AQ plus AQ. Always. You can't write it the other way. It has to be this way. If you write it the other way, you're going to get it wrong. So if something requires heat, then heating it up drives it to make more ions. You see why that makes it more soluble? If I write it the other way, then it appears like I'm going to make more solid, but that's not what's happening. So let's talk about how reactions can be endothermic or exothermic for an ionic compound. If I have sodium chloride and I dissolve this into water, I make Na plus and Cl minus, and again, we have ion dipole forming. Ion dipole forming. So how does something become endothermic? Talk thermodynamics. How is a reaction endothermic? Yeah. Yes. Did you hear that? We're talking about energy. So if it's endo, that means that the energy in the bond breaking is greater than the energy in the bond forming. Because bond forming releases and bond breaking absorbs. You need to always remember that, right? This absorbs energy, this releases energy. If something's exothermic, then the opposite's true. So if it's exo, that means that the energy in the released is greater than the energy in the broken bonds. I wrote released, but I should have wrote forming. But it is released energy. Forming bonds is greater than the bonds broken. Right? That's how you get endothermic and exothermic. Just reiterating, because you have a midterm next week. All right, so we'll go back to this slide again. If its heat is endothermic, that means it required more energy to break the solid than it did when the ion dipole formed. All right, this is showing you that if a reaction, though, is exothermic, which means that the ion dipole released more energy in forming, it's exothermic. Now what happens when I increase the temperature? It drives which way? Left. And if you followed my rule, what will happen? You'll make solid. Is that more soluble or less soluble? Less soluble. Like you're making solid. You don't have aqueous ions anymore. It's literally crashing out of solution. That's the term that we use. Crashing out of solution or falling out means that you literally will see solids falling to the bottom of your test tube or your beaker. All right, here's a solubility graph. You're definitely going to see this. This is going to be on your test. You probably will see it on the AP exam. You have to understand how to read this graph. So what's the first thing anytime you see a graph, what you should do? Read your axes, right? So it's temperature on the x, and then solubility means how many grams of solute are going into water. So as you increase temperature, each of these compounds does something different. So I'm going to ask you questions about it. These are the types of questions you'll get. Which is most soluble as temperature increases? That's easy. KNO3, because as temperature increases, solubility is increasing, right? Which of the following is going to have a decreased solubility as temperature increases? We see that, right? And likewise then, which one has increased solubility from 60 down to 40? Which has increased solubility from 60 degrees to 40 degrees? This one again. That's increased solubility. If I'm at 60 and I'm going to 40, I'm increasing solubility. That one seems to trick everybody. Here's another one. Which will precipitate the most when cooled? KNO3. What's a precipitate? That means a solid forming. Which one's going to form a solid as you cool it the quickest? This one, because the rate of that or the slope of that is the greatest, right? I say you're looking from 90 to 80, you're not going to precipitate out very much, but if you go from 90 to 80 here, you're going to precipitate out a lot. Do you understand all those questions? Okay. All right, fractional distillation is just basically like distillation, except fractional meaning you're taking individual parts of a component. So inside this round bottom flask, you have multiple substances. So you say you have A and B and C. They all have different boiling points, right? Every molecule has its own boiling point based on intermolecular forces. So you heat it up. The highest vapor pressure. Highest vapor pressure means lowest lowest boiling point and weakest intermolecular forces. That's what highest vapor pressure means, right? So weak intermolecular forces mean low boiling point and high vapor pressure. That one comes out first. So it starts to form gases. It comes up here. So say this is substance A. This is a condensing column, which means that it's cooled. So it's like an inner column, and then on the outside is tubing, and they usually send really, really cold water around it. It cools it, so as it starts coming down, it begins to liquefy. These are liquid drops that I'm drawing. And then it drops into that other round bottom flask. So once that stops forming the liquid, you take that one out, you remove it, and you put another one in, and now substance B starts coming off. And then you can separate that one and then get substance C. So now you have A, B, and C all separated based on boiling points, right? Then you can repurify them to confirm that it's actually just all A by doing it again. That's what this last sentence means, is that you can repeat this as many times as you want to keep distilling it, to keep purifying it, and make sure that it's only substance A, B, or C. I think that's it, right? Any questions?